takes a liquid metal and it draws up the tip of the needle through hydrostatic forces. And at the end of the needle, what happens is the metal sort of forms a cone. In fact, the cone has got a very perfect angle. It follows the Legendre polynomial p1/2 of theta. You know, it's exactly at the tip. It's an amazing thing. And at the tip of this cone, the electric field are like a volt per angstrom. So what happens is you strip off the ions, and ions comes out of the liquid metal ion source. But what's beautiful is when you look at this ion source, you get this beautiful, eerie blue light at the end. You know? So you see in the dark, when you look at it, all you see is this beautiful little ball of light, which is blue there. The first time I saw it, I just fell in love with it. I said, this is what I was looking for. So I started doing spectroscopy of this stuff. I put on, you know, again, this is the thing about Murray Hill. You don't go and order an equipment, right? You go to the basement again, and you get, there's this big spectrometer sitting. It belongs to Dave Aspinus, and I say, go. So I call it Dave. I say, Dave, can I borrow your spectrometer for a couple of weeks? Standard line, it's like bar line, like, you know, oh, you look so cute, that kind of thing. You know, can I borrow this for a couple of weeks, and you keep it for a couple of years, and you know, you borrow this. So he brought this spectrometer, and we did this spectroscopy of the liquid metal ion source. It was amazing, because I'd never seen stock splitting. You know, we learn about stock splitting in quantum mechanics, right? But when you take an atomic line and you put like a volt per angstrom electric field in it, man, so this is like I get a spectrometer with a slit, right? So you expect a single line that looks like this. But this line had a tail that just kept going on and on and on and on. I thought there's something wrong with the spectrometer. So I kept fiddling around with it and all this stuff. Then I realized that the real stock shift. And so I was able to then work backwards and estimate there was a really high electric field at that point, right? But then this program took a very interesting, different angle, actually. You know, so what happened was that the focused ion beam, we had to figure out what do we do with these. So we built up a focused ion beam system. We were able to produce very submicron patterns and all this stuff. And one of the real reasons for focused ion beam was because they thought that focused ion beam will replace electron beam as a mask writer or writing tool. Because with ion beams, the resist had a sensitivity 1,000 times more sensitive than electron beam. So you really had to use 1,000 times, I mean, less dose to expose with an ion beam than an electron beam. So everybody said, oh my God, you're going to write these masks like 1,000 times less time. It's really fantastic, you know, great. Problem is, statistics kill you. You see, what happens when you're going to use focused ion beam only for 1/10 of a micron or below, you're not going to use it for 1 micron. You can do optical lithography, right? So you go down to 1/10 of a micron, and then you say, okay, this is the ion beam resist sensitivity. So how many ions are required to expose a pixel which is 0.1 by 0.1 micron? And it turns out 2 ions. Imagine you have a process when you have 2 ions that are required to expose the resist. Statistically, it's going to kill you, right? So you have absolutely, you know, the process will not work, basically. The errors you'll make are just too enormous, right? So what it means is having this extra sensitivity of resist really doesn't help you. It's absolutely no help at all. So we realized that this whole great project to replace the electron beam resist was really of no use at all. So, you know, we said, we got to do something else with this thing now. So we were looking for what else can we do. So we developed these all kinds of chalcogenide ion beam resists and this and that. And by this time, I was already beginning to lose interest in this project because, like, this is turning into an engineering thing. And I was thinking to myself, hey, come on, I mean, I'm not going to do this stuff here in Bell Labs. So what happened is I started getting involved with ion irradiation of polymers. Because what happened is I realized that when you took MeV ions and you start irradiating polymers, these polymers are becoming conductive. And suddenly they become almost metallic. So I started taking all kinds of polymers, organic, anything that's organic, and irradiate the hell out of them with ions, like say argon ions, MeV ions. Ions go right through the film, they don't stop in the film, right? And then what you see in your substrates is metal. You can take these things. I mean, I had all these samples with me for 20 years, and they're still metallic, right? They look like you evaporated aluminum or something, you know? So I took things like organic stuff like bovine albumin and all kinds of organic stuff, and everything turned metallic at the end of the day, This is really fascinating, yeah. So this is to me really great. Anyhow, so let me quickly tell you that. These are the guys, the second inning at Miracle. Let me quickly finish in 2 minutes. So I guess you probably recognize many of these guys there. The first guy is my roommate, office mate for about a year. I had to put up with him. And then the second guy was David Aspinis. Then John Ford, the whole lot of wonderful guys in my department. I mean, there was really quite a crowd out there. And then the point that I really cherished was the program with Millie Dresselhaus at MIT. We had about a 7-year collaboration on a variety of things. It was absolutely nuts because Millie and I have the biggest regrets because we were so focused on laser melting of graphite and things like that. And I had the world's best mass spectrometer, and we missed out on buckyballs, right? I mean, I was using the mass spectrometer to look at liquid metal ion sources and melting graphite to look at the pulse laser, but we didn't put the two of them together. So we keep, still every time I meet her, we keep kicking ourselves under the foot, saying, what a stupid thing, we really didn't do it. So what happened in '84, essentially Bell Labs was split. I had to make a choice to go to Belcore, right? At the time, my boss was this guy on the left. His name Bob Dines, and that is John Rowell. John Rowell, if you don't know, was the guy who experimentally demonstrated Josephson junction. So John became the vice president of Belcore. This guy was in Bell Labs. So I went to and I made a proposal to John saying that I'm going to set up this big surface modification group. I need about $15 million. Do you think you can do it? So John said, okay, let me think about it. And so I was in Arizona doing my photonic experiment with optical fibers and all this stuff. Then I get a call and John says, you're hired. So I went to, we joined Belcore, and with all this fantastic amount of money that was available to us, we hired a lot of people, equipment. And then I took a 1-year sabbatical at Caltech, and then I thought I was going to come back and join Belcore, and we find that we cannot enter Belcore because the building has been, stopped by the community. They've sued Belcore, and we couldn't get in. So what I did next was, so when I came back from Caltech, we had nowhere to go. I had to house 10 scientists and $50 million worth of equipment, and nowhere to go. So I had only one option. I went to Rutgers University. I asked them, who's the guy who makes decisions on the campus? This is the guy, Alec Pond. He's the guy who cracks the whip. So I called this guy and I went to him and said, look, here's the deal for you. You give me a place in Rutgers for, say, 2 or 3 years. By the time you leave, I'll establish a center for you here in surface modification. And within 2 months, they cleared off the basement of this building. It's a sterile physics lab. 5,000 square foot of space was created for me. We moved all our equipment, people in, they put temporary buildings outside with the trucks and everything moved in. And we got offices. John Rawls couldn't believe that we got all this space here so quickly. So we were in Rutgers for 2 years or 3 years then. And that's why we discovered PLD process basically, right? That's when we were at Rutgers, actually when we invented the PLD thing. And very interesting stuff because I was at an Anaheim meeting, MRS meeting. This is in 1987, right after the ITC, and we were discussing over lunch, all these guys, and I'm telling, hey, listen, guys, the biggest problem people are having is getting the composition right. What if you take a pulse laser? We were doing pulse lasers, various things with pulse lasers. Why can't we just evaporate the stuff? Maybe we'll get the composition, non-equilibrium evaporation. And basically, everybody said, no, it's not going to work. All my guys, they're all sitting down writing equations as to why it shouldn't work, right? And you go and do this experiment. This is an experiment done in air, basically. Put a 1, 2, 3, put a carbon foil, and we evaporated the stuff. Man, this thing worked. And we figured out how, all the issues like angular dependence, energy density, and all this stuff worked out fine. But then I made a proposal to the Belcore, we should really focus on oxide, because that's where the future is. And I put up this thing that Daryl remembers this slide, right? I know that. Yeah, anyhow. So I said, look, the future is going to be like this: superconducting electronic, VLSI, compound semiconductors. You're going to be sending information, gigabits coming in information and going out like this stuff, fiber optic stuff. Well, my Belcore management knew something that I didn't, that this company was going to collapse one of these days, which I didn't know. So anyhow, they were not very supportive. In fact, Ramesh and I tried a lot of different things, but it wasn't really moving. So that's when I formed Neosera, my own company, and today Neosera we do PLD, PED, and we have several products, many of which we have sold off today, and we are only focusing on 3 businesses: PLD, PED, and Magma. And Magma is doing some remarkable things now. We can do, this is a 8 or 10 stack silicon die, and we can actually image the current across this multiple die stack. You can see the current path. We can measure this with magnetic microscope completely. And the most remarkable discovery is the fact that we're able to operate the squid at something like 500 megahertz frequency, which has never been done before. And we're able to image actual currents. There's a break in the line here. See, the line is broken, but I can still emit the current because I'm using high frequency current. And so you can actually locate and open an electrical line to a precision of, like, say, 10 microns or better. The nearest technology today is time domain reflectometry with a 1 millimeter resolution. So this is really, truly what I call a breakthrough technology. But anyhow, you guys already heard from Maryland. After Belcore, so I went to, I left Belcore at that point because I realized that this place was not going to satisfy my vision. I went to Maryland, and then this is all my students. I'm really proud of them because there are roughly about, I think, 11 students of mine. Among them, they've started about 17 or 18 companies, just these guys, actually. This guy in the corner, his net worth is over a few $100 million because he's the, owner, one of the owners of Deloitte and Touche consulting company, anyhow. So this, and Shindy Wu, he's one of my co-discoverers of PLD, and he's now he runs a VC fund in Shanghai. So each guy is very interesting in life in themselves, basically. So this is you already heard about it. So that's why I decided to come to move to NUS. I would like to correct Barry Hallowell because I didn't come for an administrative position, actually. It was advertised as it was actually Barry's job that I came for. So it was advertised as the deputy president for research. That's why I came. I didn't think it was. But when I came here, the president told me what was involved in the job. He said, it is deputy president for research. But he described all the administrative thing that I had to do. And by the time he finished describing, I said, I'm in the wrong job. This is not what I wanted to do. And so they worked out a completely different thing for me, which is really what I wanted, actually. So that's how I came to be an institute. So I report to, so this guy, Fong Shi was the one who hired me. But after hiring me, within 2 years, he left to become the president of KAUST. And Chor Chuan is the guy in glasses. And the next, and the other 2 guys are the deputy presidents, Barry Hallowell and Eng Chai. And these are the 3 people to whom I report to right now. So that is the sort of thing. This is our NUSNI. I formed Nanocore, but after that, they integrated several organizations under us, NUSNI, Nanocore, SSLA, SIBA. All of these facilities are under one right now, and which is pretty exciting. And this is Nanocore that many of you will be seeing tomorrow. All I can say, the best is yet to come. It's fun. I'm sorry if I took up your time this evening, but I just wanted to say this. Okay. So all I can say is, hey, listen, do what you really want to do. And Thank you.
Thank you for the session on the celebration of Venky's 65th birthday. And now we have some administrative announcements.
Yeah. Great. So I want to, on behalf of the judges, I want to announce the 4 winners of the poster competition. And part of your prize is that you get to present 3 view-graphs and speak about them for no more than 3 minutes tomorrow. So that's why I want to give you this warning right now. So the 4 winners of the poster competition were number 40, number 54, number 81, and number 96. So tomorrow, yes. sorry. You'll see tomorrow, yes. You'll see tomorrow with 3 views in no more than 3 minutes. And the last thing I'd like to announce is actually next year's WOE will not be here in Singapore. Thank you. It will be in the U.S. It'll be in upstate New York. So I hope that you will all come and bring your friends. It should be right around in the fall, around fall colors in upstate New York. The location is about 1 hour north of Albany. You can see that on here. If you're thinking of flying there, Albany is the capital of New York, so airplanes do go there. You could also, you could if you wanted, you could fly to Boston or New York City, and that's about a 4.5-hour drive to the conference site. What else do I want to say? Okay. Anyway, you see the conference site. Look forward to seeing you next year in upstate New York. Thank you.